topic today is polar molecules. Okay, so when I am talking about polar molecules, I'm talking about molecules that have a charge. They have poles. They've got a positively charged portion to the molecule and a negatively charged portion to the molecule. Okay, so what we need to do is we need to figure out how to tell whether or not a molecule is polar. Now you might ask me, who cares whether a molecule is polar or not? But what you will see from an activity that we will do in class, that it affects quite a few characteristics about a molecule and the way it behaves, whether it is polar or not. That will come in time. Okay, so the first thing is in order for a molecule itself to be polar, it's got to have polar bonds. If there are no polar bonds in a molecule, then the thing is going to be nonpolar. The molecule itself is going to be nonpolar. Now, how do we determine whether or not a bond is polar? We say that if the difference in electronegativity between the two bonded atoms is less than 0.5, then we say that it is nonpolar, that the bond is nonpolar. So if we look at a molecule like methane, look at a molecule like methane, the only kind of bonds that methane has are carbon-hydrogen bonds, right? And the carbon-hydrogen bond is not a polar bond. The difference in electronegativity was 0.45, I think, right? So less than 0.5, less than that critical threshold. And so we say that carbon and hydrogen shares their pair of electrons equally between them, okay? So there's no polarity here in this bond. There's no one atom that keeps the electrons around itself more often, giving it an overall electronegative charge. So, because methane is made up of all nonpolar bonds, this is a nonpolar molecule. It will not have a positive and a negative region to the molecule. It is nonpolar. All right. So again, methane is nonpolar because it doesn't have any polar bonds. 0 polar bonds. Now, okay, so let's go ahead and write that. If a molecule has no polar bonds, it will be nonpolar. For example, methane, CH4. All right, now molecules with polar bonds may or may not exhibit overall polarity. So it depends. Yeah, it's got the polar bonds. Okay, so it's setting up dipoles. But the whole thing may or may not be polar. So how do we know? How do we know whether or not a molecule with polar bonds is actually a polar molecule? Well, geometry. So shape determines whether a molecule with polar bonds is polar. Okay. Let's talk about some jargon. Some vocabulary that is specific to this. Okay, molecules that are polar can be referred to as being polar, so it's a polar molecule, or they can be referred to as, so molecules that are polar can be referred to, it's just one F, isn't it? Yes. As being dipolar. So it's a dipolar molecule, which seems a little redundant to me, but anyway, you might see that. Or to have a dipole moment, which is about the silliest jargon I've ever heard. So, molecules that are polar, sometimes you'll hear them referred to as being dipolar. It's a dipolar molecule. Or you will hear it referred to as being a molecule that has a dipole moment. So, polar molecules have a dipole moment. Okay, let's see, what else? The dipolar character, or I'm just going to say the polar character of a molecule is represented by a funny little arrow, is represented by an arrow. Okay, and the arrow looks like this. Here. This end of the arrow is the electropositive portion, C positive, and this end is the electronegative portion. So, if you ever see this arrow, you'll know that it's pointing towards the electronegative portion of the molecule. All right, now, how do we determine? Okay, we're going to go over your entire shape table tomorrow, but I would kind of like you to to see if you can't figure this out on your own, the rest of the shapes. I'm going to just do a couple of things right now. Okay. So, for instance, HF. Okay, this is a polar bond, hydrofluoric acid, or hydrogen fluoride if it's a gas. And, okay, so, you guys, this is going to be the electropositive portion. This is going to be the electronegative portion because fluorine has a greater electronegativity. So it's going to keep the electron cloud around it most often. Or the majority of the electron cloud, I guess, will be here. And so this is a polar molecule, the electropositive end, the electronegative end. So we say that it's dipolar, it's polar, or it has a dipole moment. So, it has a dipole moment, just for fun. Let's say it, write it. Okay, this is a polar molecule. All right. Now, this is where things get to be a little bit more tricky. Okay, so we've got carbon and oxygen. Okay, and these are both polar bonds. Okay, this is a linear molecule, so it's all in one plane. It's linear. Okay, so the electropositive carbon is in the center, and then we have oxygen being electronegative, oxygen being electronegative, right, and the carbon is electropositive. It's got two polar bonds, but is the molecule polar? No. The molecule is not polar. And why is that the case? So I'm going to write nonpolar. It doesn't have a dipole moment. And why is that? That is because the midpoint of these two electronegative portions is where? The midpoint of these two is here, directly on the electropositive portion of the molecule. And so they cancel, giving the thing overall nonpolar behavior. Okay, so again, you guys, these electronegative portions, okay, what is the midpoint? The midpoint is directly here on the electropositive portion, and because remember, we are in a line, and so they cancel out, and that ultimately makes the thing nonpolar. Okay, I have a cute little tetrahedron here. Okay, but we'll go over this in class as well, but I'm just going to do it here once. So, let's say that these are all polar bonds in this tetrahedron. They're all polar bonds. So clearly it's not methane, right? Okay, so, because they're all polar bonds, this might be a polar molecule. But, let's say all of these ligands are the electropositive portion, and the central atom is the electronegative portion. Okay, what is the midpoint in three-dimensional space of dimensional spot as the electronegative central atom, and so it will cancel out the polarity. But what if it's pyramidal? Like this, right? And, sorry, let's move that on here. And this would be our lone pair right here, okay? So ammonia, for instance. All of these are polar bonds between nitrogen and hydrogen. Electropositive, electronegative. Where is the midpoint? Is the midpoint here? No. The midpoint in three-dimensional space is a little bit below it, right? And so the positives and the negatives don't cancel out because they don't. The midpoint of this electropositive is here, not directly on this. And so ammonia is a polar molecule. Water. Here it is. Hydrogen, hydrogen, oxygen, electronegative, electropositive, electropositive. Okay, what is, and so, polar bond, two polar bonds here. Where is the midpoint of the electropositive? The midpoint of it, you guys, is right here. Right here. And so, that very much makes water a polar molecule, because the positive pole being here, the negative pole being here. They don't lie on the same plane, so they don't cancel each other out. All right, so tomorrow we'll go through the whole shape table and determine which of those shapes are going to be polar and which ones are going to be non-polar. And we're going to do an activity, and we're going to look at kind of bigger molecules too that have little polar tails. All right, that's it.